So hello everyone, I'm Hannah, a researcher from UC Berkeley, Skylab. Today I will be talking about CacheCatalyst, enhancing web caching for the latency constrained internet. This is a joint work with Mohammad Hosseini from Shahid Beheshti University, Sina, Darabi, and Patrick Eggers from USENIX, and Mohammad Choopani from Shahid Beheshti University and Skylab UC Berkeley. So, caching is what that makes the web feeling fast. So basically, when you click on a link to a page that you've been on before, your browser doesn't re-download the page. It pulls dozens of resources from a local cache, and most of the bytes, they never even travel over the network. So caching works. But the question here is, if everything is already cached, why does a revisit still take so long? So to answer that question, let's compare what happens at protocol level between a first visit versus a revisit. So when you do like the first revisit, the browser asks the HTML. Then for each link resources, it's going to basically fetch it from the server. So every response carries the content, everything looks good. But now if we're going to see what happens at the revisit, the browser actually has all these resources, but it still is going to, let's say you came back 2 hours later to the same web page. So your browser has everything, and then the server, but you still are going to ask the server, is it fresh or it's modified? So each red arrow is an if non-match request, which it basically is a response is true or for non-modified. No content at all has been served at these errors. It's just checking with the server whether the contents that you have, the files you have for each one of them is fresh or not. So if you see, there are many red arrows there. Most of the time on a revisit is just a round trip that delivers nothing except just confirming what the browser might already have. And that's the problem. Many big companies, like for example, Amazon and Google famously reported that 100 milliseconds of a delay could cause them and cost them 1% of their revenue. So what a good solution looks like. So a good solution would be we cut the round trips on revisits. We make sure that we do not waste bandwidth, and then we preserve end-to-end security. And let's look at how the existing approaches, they are compared to these three solution metrics. So starting by standard HTTP cache, we just saw that there are too many RTTs, so it doesn't cut the round trip times. The conservative TTLs, that the time to live, that are basically set by the developers, they're not going to help in revisits at all. In addition, anyway, you're going to download that page after the TTL is expired. So we're going to have the bandwidth waste as well. The closest solution is HTTP to server push. So it's going to resolve the RTT, but then because in HTTP2, the server is going to push at the first response all the content of the client side, no matter if they are fresh or not. So still we're going to waste the bandwidth. So in this work, we try to solve these three using CacheCatalyst. And let's see how. So one thing that I want to be clear about is that basically compared to 30 years ago when HTTP was designed, back then bandwidth was the bottleneck, but now today latency is the bottleneck, and we have a huge shift. So to do that, we measured across 5G 5G speed, like with 60 megabit per second speed across 10,000 top websites that has been basically visited. So now we want to know why latency dominates. So we measure the download time and round trip time across thousands of resources on a real ADSL and 5G connections. Each curve is a CDF. So for curves total, but here I focus more on the 5G because that's what is basically more important in modern users scenario. So if you look at the real curve, the tail curve is the download time on 5G. The red curve is the round trip time on 5G, and you see the download time is, even for ADSL, it's always on the left side of the RTT. So basically on 5G, the median round trip is 2.6 times higher than the median download. Even when the content is being delivered, the round trip dominates the time on the wire. So now, if we want to think about the revisit, and then what we see is that actually it's going to get worse. The other thing about reloading a page is critical path. So basically the graph that has the index HTML and all the contents that they depend on it. So the critical path of a page is the longest chain of dependent fetches. So if we can shorten that, then the page is going to load faster. So we measure what would happen if we removed every non-modified round trip. So the x-axis is how many RTTs we've saved, and the curve shows this across the whole corpus that we did, like the same with the previous slide. So the average page would lose about 56% of the page load time. That is just the ceiling, that's what possible. But the question is now how to capture it. So here's the question that kind of motivated our design. And so if most resources haven't changed, why are we asking the server one resource at a time? Well, we shouldn't be. We should actually validate the whole cache once on the HTML request and then decide locally for everything else. That's the main idea behind CacheCatalyst. Now at the protocol level, let's see the overview of CacheCatalyst. So the browser sends a get index.html, same as what happens today, but adds a new header called xcache resources. It carries the URL and e-tags of resources of the browser that already has cached for this page. And then the server returns the HTML and adds x validated, so for each cached resource, whether it's fresh or it has been modified. So after this single response, the browser knows the validation status of every cache response. For example, here the CSS file is still fresh, the JS is fresh. The only thing that has changed is the JPG that the server is going to push it to the client. So that's the entire protocol. We just added one header up and one header down, so no new round trips, and then we even didn't touch the TLS connection, and we still have the end-to-end security. So if I want to just summarize what CacheCatalyst does in 3 steps. In the first step, we have pre-validation. Basically, the browser piggybacks e-tags of cache resources on the HTML request. Server replies with a fresh or stale flag for each. Then the browser is going to decide that locally. So browser uses fresh entries straight from cache, no extra validation request is required, so no more 304 round trips. And then it pushes the deltas. So we have cache aware push that sends only resources to the client that are truly has changed. So it avoids bandwidth waste as well, which actually was the first reason that the HTTP push was killed before, especially on, as far as I know, on Chrome and Firefox. So we don't have that issue here. But let's see how we're going to realize CacheCatalyst in real world. So basically, we're using the Service Worker API. Every major browser supports it. So the service workers are going to sit between the page and the network and can intercept requests. So we deploy a service worker with the CacheCatalyst logic. It maintains its own cache with e-tags and handle the new headers. On the server side, we modified Caddy to recognize the headers and produce the validation response. So server change is small, around a few hundred lines of code, 500 to 600 lines of code, and then the browser change is 0. So the design is kind of clean and small. And now let's see actually how it's going to work. So to evaluate CacheCatalyst, here is the setup that we used. So we actually pulled 10,000 pages from top 100,000 websites, not just the home pages, but we also dig deeper to deeper pages as well. The server is modified Caddy. The client is a real Chrome through Lighthouse. So we measured 6 perceived metrics plus traffic overhead. These 6 metrics are basically widely accepted as more representative of how the actual user experiences than the page load time alone. So if I just want to go over them really quick, so we have PLT, which stands for page load time, and it's click to the last byte, and first contextual paint, which is first text or image that is going to be visible, LCP, which actually page looks essentially done at that level, CLS, basically when the website is visually stable, speed index that shows how quickly content fills in, and time to interactive or TTI, that when the user actually can click on the content of the website. So these are the metrics that we considered. We also considered the test under 12 network conditions, 4 bandwidth level by 3 latency levels. So bandwidths from 0.5 megabyte per second here, which is a dial-up territory, and up to 16 megabit per second, which is a fast 5G, and latency from 40 milliseconds, which is the fast home connection, to 200 milliseconds, which represent the slow mobile. And then we do this across reload delays from 1 minute up to 1 week, plus the new page on the same site case. So if we look at this graph, basically it shows RTT reduction by reload interval with and without cache-aware push. So basically, we have CacheCatalyst, the basic mechanism, and then we have CacheCatalyst plus cache-aware push, which actually gets the concept from HTTP push, but it's smarter because it's not going to send the whole content to the website, but to the client, but it just checks at the server level and sends basically whatever that is that needs to be updated. So the teal bars kind of decline as cache ages. So this is expected. And the hash bar sits kind of higher than the teal bars at every interval, which actually means the cache-aware push helps on top of the base mechanism that we introduced. So the take from this website, this result is 3 numbers. So in the best case, when the preload is just for 1 minute and we have the most common revisits, we see that the median RTT reduction has been reduced by 78%, and under the worst case, at 1 week, the least median across all intervals is 53%. And on average, the RTT eliminated per page is 4.3 times better. So it means, like, for example, on a 5G connection, if RTT is about 100 milliseconds, it's like we're saving 400 milliseconds on average, which is huge. So now if we want to compare CacheCatalyst with server push, which is basically the closest existing solution, the x-axis basically lists the 6 matrix. Each measures a different part of how the page feels to the user, as I mentioned before. And then if you look at the page load, both methods give up about 40% improvement at PLT. But when it comes to FPC, LCP, and for clickable or TTI, actually we have median improvement of CacheCatalyst by 28% and 37% for LPC, and for TTI actually this is negative for server push. So now in terms of overhead, if we want to compare the CacheCatalyst and HTTP2 server push, so CacheCatalyst overhead is just the validation headers that I discussed, but server push overhead is everything it pushed and the client didn't need it. So for CacheCatalyst, as you can see, it's about 1.5 kilobytes per second, and for HTTP server push, it's more or less on average is about 1 megabyte per second. So we actually are kind of 1,000 times less in terms of overhead. That's why CacheCatalyst is kind of practical to deploy and to be considered for massive deployment and is scalable. So if I just want to summarize what we had as takeaway for now, we saw that today the bandwidth is not the bottleneck, and it has shifted. Basically, latency is the bottleneck. So based on that, we try to introduce CacheCatalyst that wants to validate the whole cache once on the HTML request and decides locally for everything else. And we saw improvement of 40% PLT, 37 LCP, and 28% FCP, which is basically what we have done compared to server push. The code is open source and available if you want to try it yourself on GitHub Turing Lab. And now at the end, so let me address the 3 main limitations that we have here which are not going to be blockers for CacheCatalyst, but they need like deeper work. So basically, in all these three cases where the mechanism doesn't deliver its full potential, so for the first case, navigating to a page on a site we've already been to, the mechanism still works, but our early validation list doesn't always cover every resource the new page needs. So the missed resources fall back to the traditional conditional gets as introduced by HTTP, but basically the future work can improve the resource convergence. And the second is CORS, which stands for Cross-Origin Resource Sharing. It's a browser security rule that controls when a page can read a response from a different domain. Some third parties resources fetched at runtime by JavaScript, like for example, analytics script, can return our basically validation responses if their origin enforces strict CORS. So crucially, this only affects on script fetch resources, but the other kind of resources that are directly embedded in HTML, like images, style sheets, and fonts, they will remain unaffected. And the third one is when sites that already uses a server worker for other things needs to integrate our caching logic as well. And so a native browser implementation would remove this entirely, and we hope actually that this becomes part of the HTTP itself. So, and also the other thing is some of the websites, they block the server, some of the servers, they block service workers all at once. So thank you very much, and I'm happy to take questions.